record this. Okay, well, welcome to our webinar for the NIST community, NIST-funded Center for Risk-Based Community Resilience Planning. The title is Using INCOR to Study and Measure Community Resilience. So just we ask you'll be muted if you're not a presenter, just for organization. So I'll ask that you use the Zoom chat to ask any questions. You can make comments, have dialogue. I think we're all used to this by now. So today's topics are just a quick overview that I'll give now. We'll talk about the Seaside testbed. Dan Cox will talk about that, followed by a demo by Jung-Sung Lee of NCSA. We'll move into Galveston, and then we'll look at Joplin, Missouri. Galveston will be presented by Jamie Paget, and Joplin I will present. And then we'll have Q&A by Jamie Cruz and Jared Lorzell. So Presidential Policy Directive 21, PPD 21, defines resilience somewhat comprehensively, but within that is the ability to prepare for and adapt to changing conditions and to withstand and recover rapidly from disruptions. And so today, we hope that you'll see three different examples for three different hazards in three different locations in the U.S. that demonstrate the ability of INCOR to do all of these things that you see in red. The National Academies of Science, Engineering, and Medicine in 2019 called for a new type of research that is needed that can address the dynamic state of communities and their changes of risk, but in particular, their resilience over time. So resilience is a temporal process or a process that it can also link information from disparate programs, so data-driven models with physics or process-based models, and then link this research and the data and bring it all together for decision-making and decision support. For those of you not familiar with the NIST Community Resilience Center of Excellence, we're beginning our 7th year. The development of INCOR was front and center in the first 5 years. It still is, but it's moved from this knowledge creation to knowledge implementation and taking it all the way into decision support for measurement science and decision making. So the process that you'll see today is we begin by developing an integrated community model. And so here you can see a power network, a water network, transportation, of course, buildings, which are key, and all the physical infrastructure, some others as well. Then that combined with a model of the economy, as well as social institutions and households. And together those make up the community model. So then once we have that, once we have that integrated community model, then we then move to the damage and loss analysis, which is the impact of the natural hazard on the community, and then modeling an interdisciplinary recovery with fully integrated supporting databases. And the ultimate objective is how do we enable the analyst or the community leaders or the researcher to look at alternative actions so that they can enhance their community resilience and inform planning decisions. So I won't go through this, but this is in too much detail, but this is the conceptual structure of INCOR. So what you'll see in the notebooks will pretty much take us all the way to about here. It'll be this portion. And then we hope in 6 months, or excuse me, in 1 year to be able to, then we'll have this coded, this last optimization part will be available in the next release of INCOR, which you'll hear about shortly. And so some of the key features are that the resolution INCOR operates at the building or the household level, and that enables combining physical infrastructure with the social science algorithm. And so this is a cross-disciplinary dependency. network systems, water networks, electrical power networks, they also operate at a detailed component level so that they can link to household dislocation and other social science-driven models. For hazards, you'll see the two different tiers that we have today. The tsunami hazard will be a tier 2, as well as the hurricane hazard, and the tier 1 model, you'll see that that will be the tornado hazard. There's also functionality modeling models. For functionality, they're very flexible, can be user defined, and can include dependencies on networked infrastructure. And then advanced economic models, a computable general equilibrium model is used. And this is an advanced state of the science modeling of economic systems within communities. And then a policy portfolio that's forthcoming. And so you won't see that today, but in our next demonstration webinar, we'll be able to look at what if scenarios and explore those for community resilience planning. And then finally, optimization and decision support. As I mentioned, this is coming again in the next release. And InCore allows robust temporal and spatial analysis. And so it ultimately allows users to time step rather than just using trajectories that can't be changed. And this allows the analyst to consider the effects of policy options at key points during the recovery simulation. And then there's suites of fragilities available, and you'll see some of those used in the demonstrations by Jongsung Lee. So measurement science is implemented in InCore. This is open source, available on GitHub. There's a landing page, which I believe you'll learn about in the webinar shortly. Excuse me, in the demonstration within the webinar shortly. And today, we're going to present, as I mentioned, Seaside, Oregon, Galveston, Texas, and then Joplin, Missouri. And so with that, thank you, and want to acknowledge numerous researchers that have contributed. And today, as the presenters, were the testbed leads, but simply just the messengers of all the good work done by the students, postdocs, and people within the center. And so with that, I will stop sharing and pass.
Okay, John, you ready?
Yes, please.
All right, I'm going to try presenter mode, and if it doesn't work, we'll just go back to this way. You can let me know how it looks. Looks kind of dark. That didn't work. How about this one?
Yeah, we can see that.
Okay, perfect. So hello, everybody. My name is Dan Cox. I'm a professor in civil engineering at Oregon State University, and I'm going to provide an introduction to the Seaside testbed and a little bit about the geography and demographics and economics are written on this screen here. But in general, this is a small town in the Pacific Northwest facing the Pacific Ocean. About 6,000 plus people, kind of a steady growth rate over time. You can see a little graphic in the lower left-hand corner over the last 100 years. So it's growing steadily with permanent population. And then it also grows dynamically over the weekends with probably about a tripling of the population just from the tourism that happens there. But it's been a small town, or it is a small town, which makes it convenient for this type of work, putting together a test bed where we can start to look at the parcel scale. So that was one of the big pluses. And then the other one is that it's been identified as vulnerable to the Cascadia subduction zone threats of seismic and tsunami hazards. You can see the graphic on the left is showing the position of the Cascadia subduction zone. So it's sort of right in the middle of that giant fault. People have said that if this were to happen today, it would be the largest natural disaster in US history. You can see the picture on the right-hand side is showing a picture from the Japan tsunami in Sendai. So it's comparable to that level event, about 8 meters of water on the shoreline and then rolling inward. So we have a lot of work to do to prepare for this event. And I'll just talk a little bit about some of the data that's gone into the test bed that's in INCOR for people to use, starting with the hazard. We did a full probabilistic seismic and tsunami hazard. So we have consistent sources for the earthquake and the tsunami. And then we're generating a suite of hazard intensities that are important for looking at the effect on the built and natural environment, things like peak ground acceleration, displacement, and then the different properties of the tsunami, like flood depth, velocity, and momentum flux. And then because we were interested in risk-based analysis, we looked at these different recurrence intervals spanning from 100-year all the way out to 10,000 years. So these are all provided as shapefiles in INCOR to be used. One second. Okay, there we go. And then as John mentioned earlier, we also want to have a complete community description. And so I'll talk a little bit about some of those things that we have, for example, starting with the parcel level building descriptions, using tax lot information, for example, Google Street View and boots on the ground. Just trying to pinpoint exactly what type of building we have everywhere within the town, also identifying where the critical facilities are. And then also being able to use that, and you'll see in the demonstration how we can use parameterized fragility curves to look at damage and then ultimately risk and dollars lost. So it's just a graphic just showing, for example, being able to deaggregate based on earthquake, seismic and tsunami, and then the combined results. We've also identified several networks. So for example, the bridge and road network, the electric power network, the freshwater network, these are all provided in INCOR. Not everything is complete. So for example, the transportation network is just roads and bridges. The power is just electric power utilities and substations. And then the water network, for example, is freshwater pipes and pumping stations. But it's a good start to look at things like connectivity and connections between these different types of infrastructure. And just like the building damage, we can also start to look at the damages as well as the uncertainty behind those damages across these different mean recurrence intervals. So we can start to quantify the risk, for example. All that can be done within INCOR. And then we also want to have descriptions of the socioeconomic portions of the community. So for example, where the people are, the number of people in each of the different households, and then also looking at the value of the infrastructure, for example, real market value of the buildings. That's also shown on this graphic. And then as John mentioned, there's also CGE modeling. So that's been developed for Seaside. It's been partitioned into 3 different zones based on the geographical regions. There's an area that's closest to the coast, in the middle, and then to the east. Some of the ongoing work that we're doing is, in the development of INCOR, is trying to look at things like operability and connectivity, as well as restoration. Some of this is tying, for example, the outputs of INCOR with other models, for example, to look at debris and debris advection. And then a lot of this work is being developed within Jupyter notebooks so that users can get up to speed pretty quickly. And that's one of the things that John is going to demonstrate next. One last thing before we get to the demo is also looking at things like optimization, for example, of mitigation alternatives. So for example, looking at either retrofitting or relocating buildings, for example, to minimize damage. So that's also some of the ongoing work. And with that, I'm going to turn it over to John for the demo, and he's going to talk through type of analysis that you can do with this Seaside testbed in INCOR. So John, with that, if you're ready, I'm going to hit the play button.
Yep, I'm ready. Okay. Before moving into the actual demo, I want to show you that this is incor.ncsa.illinois.edu page, which is INCOR manual page. You see that all 3 testbeds is already published here as a documentation. And also you can find the zip file on the page. You can download, you can able to execute those Jupyter notebook on your machine also. So please visit. So Seaside Jupyter Notebook, this is the demo we're going to show you, this actual Jupyter Notebook. You can see that there's some background of those things already Dan explained, the regions and those hazard models we already explained by the Dan. And you can see that we have multiple recurrence intervals we are going to use on this analysis. So you can see there's 3 layers for tsunami and earthquake for each recurrence interval years. So we are going to already this information publish it to our hazard service. And this is the building inventory layer. So as usual, as you're familiar with INCORE, we're going to import those modules for the analysis. And then these are the already published layer on the hazard services that you can use. So you can use that ID for earthquake or tsunami or recurrence interval, you can use it. So this is how you defined in the Python, that you can define the years and actual ID that you can use on the analysis. So we're going to do damage analysis for earthquake. Interesting thing, you can see that there is a for loop that goes through that recurrence interval and then run the same building damage analysis very simple way. So you can see in the code, there is a hazard ID you can see here. This is replaced by the for loop. So it runs for each recurrence interval and then also store the result in the list data structure in the Python. So I have to run it and it runs for each recurrence interval. And then same way, we could do the tsunami building damage analysis too. You can see the interesting part here is the code is very similar, which because we are using the same API, so that you can, differences here is we're just replacing the hazard IDs here. Same way for the earthquake and tsunami. So in short that building damage analysis in PyIncore or INCORE supports a multiple hazard models. So after you run this, and then we're going to look at now combined or cumulative building damage analysis. This is a kind of chained with the previous analysis you just saw. So what happened here is you can see that in the code, input parameter has earthquake damage outputs and also tsunami damage outputs from previous run we already done. So we're going to use these 2 outputs to compute cumulative building damage. So the same way we run this. After the run, what we're going to do is we're going to show you the quick visualization of mapping. So we're going to show the cumulative building damage of the 50 years of recurrence interval. So you can see this is the output we have, and then we create this data object, and then you can run this. PyIncore has a visualization platform that you can show that this mapping. So you can see the some of the damage states here, and you can also zoom in certain area. You're able to look at more detail. These dots show the centroid of the parcels of the building inventory we have for city of Seaside. And the next step we're showing you is Monte Carlo simulation for functionality of the buildings. So what it does here is that we're going to run Monte Carlo simulation for this failure state keys, which is damage state 1, 2, and 3. So when you fall into this damage state, we classify as a failure. So you can change that also just for damage state 2 and 3 if you want to. And then for each recurrence interval, we also run this analysis. So you can see that it runs for each of them. It takes actually longer, but I edited the video to make it short. After that, we're going to look at the result. When you do the visualized result, we are using Python pandas library to do. So you can see that we're already using those outputs from the previous analysis, and we're going to visualize this output as a table. So what you're going to see here is a combined table to show that for each buildings, it rows each building, and each building has this failure probability for different recurrence interval here. We only show 5 rows here, but it actually calculates for entire building inventory. And also you are able to plotting the histogram using the matplot library and the Python too. So similarly, we are using this and create a histogram. And now you can see this as a grid view. So each row shows earthquake, tsunami, and also cumulative building damage analysis. And then column shows 500 years, 1,000 years, 2,500 years. So you see that these damages are combined in the cumulative analysis here. So this is one of the example of a various way of visualizing it. Next one is, this also shows the possibility of how you can model your own using the PyIncore or InCore. So this one shows that the researcher create the expected economic losses analysis based with their own equation, but using all the result coming from the InCore and also create these outputs here. So you can see here, there's a black line is earthquake, and then black line is cumulative, and then blue line is earthquake, and the red line is tsunami. So it shows that economic losses per return intervals. Next one is similarly, it does the economic risk. So it's defined as a losses times the probability of occurrence. So using that equation, you can still do another analysis. And this is output of the economic risk for this system. That's it for the seaside demo. Thank you. So next will be Jamie Pezeff going to present about Galveston testbed.
All right. Hello, everyone. Can you hear me and see my screen okay?
We can, Jamie.
Excellent. Well, I'm pleased to share with you a brief introduction on the Galveston testbed. This is the newest testbed that you'll find within the NCORE libraries. And Galveston is essentially about 50 miles from where I'm sitting at Rice University. It's along the southeast Texas coast, and it's been subjected to a series of severe storms and hurricane events over the past century. Of note, our testbed is primarily focused on the city of Galveston within Galveston Island, but also looking at connectivity to the mainland as well as to the Bolivar Peninsula. I wanted to briefly touch on some of the background and motivation for selecting the Galveston testbed and some of the opportunities for building upon and leveraging this testbed. One is our interest in investigating multi-hazard effects in a coastal community setting with exposure to multi-hazard storm events, looking at effects of storm surge, wave, inundation, and wind hazards. A second is the interest in exploring interdependent infrastructure systems in these coastal settings, such as buildings, transportation, and power systems. We had the opportunity to leverage historic social scientific data that have been collected following past events, in particular after Hurricane Ike, which struck the region in 2008. And we're leveraging this testbed to evaluate various hybrid metrics of community resilience that require coupling across these different systems, such as between social and physical systems. Some of the early data sets and models that are in NCORE are listed here, and we're continuing to work and expand and populate additional models and data libraries as you're looking towards future NCORE releases. What you'll find today would be hazard models with respect to storm surge, wave, and inundation, models that would support the built environment in terms of the physical infrastructure data, like building or transportation related data and associated damage analyses, as well as household level data, implementing a model for housing unit allocation and population dislocation of around 32,000 households in Galveston Island. Just to take a look at each of those in a little more detail, I just wanted to show you a brief overview of one example of the types of hazard models that NCORE supports. One would be this potential for ingesting the output of high resolution or high fidelity simulations of coastal storm hazards, where we have pre-populated rasters and outputs of hindcast of past events like Hurricane Ike, as well as scenario storm events such as a 50-year, 100-year, or 500-year return period event. And this would allow us across the spatially distributed region to estimate intensity measures like storm surge elevation, wave heights, or inundation durations, which are important for looking at some of our coastal environment damage functions. INCOR has the potential to support parameterized fragility models, and this is a relatively recent feature of INCOR as we shift from perhaps traditional fragility models with univariate predictors, especially in some of these coastal multi-hazard settings. It was important to be able to support parameterized models that consider, for example, combinations of hazard parameters such as storm surge elevation or wave height, as well as characteristics of our built environment, with the example here showing the residential building fragility models that also would depend on features like age or elevation. And you see an example here of those models applied for 19,000 residential structures, and Zhang Li will show you their application in a Jupyter notebook in the demo that's forthcoming. Another feature of INCOR's ability to support parameterized fragility models is also to help us to build up those constituents of some of our infrastructure networks. And an example here would be coastal bridge fragility models, which were analytical fragilities derived based on surge and wave loading on these structures, with our parameterized models looking at the potential for deck shifting or unseating based on hazard intensity and structural characteristics across the region. And a last example of that support for parameterized fragilities would be a recent model developed for coastal roadway damage. This was an empirical fragility model developed based on satellite imagery, field inspection data, and storm hindcast data that are applied at the network segment and then aggregated at the link level to support network analyses across the region. You'll also find in the Galveston testbed the application of various social science models. One example here is the housing unit allocation model, which builds on the concept of intersectionality theory that allows us to go at the resolution of the household level to look at that intersection of race, ethnicity, or income, which can support different types of analyses, such as looking at population dislocation at that household level. So here's an example of a model that's supported that was derived based on field study research with an empirical basis for validating some of these social science models, and that combines features from the built environment damage as well as that empirical data. And through INCOR, we can explore these either in outputs in tabular format or as spatially visualized data with interaction. Just want to note some of the ongoing and future work that you'll see in forthcoming releases of INCOR would be adding additional infrastructure systems and network analyses under multi-hazard conditions, looking at features such as population return or household recovery and additional restoration analyses, leveraging this test bed for social institutions modeling, as well as building a future CGE model for economic analyses in the region. So with that, I'll pass it to Zhang Li for the demo of the notebook in Galveston.
Could you play? Thank you. So this is a Galveston testbed notebook. As before, it shows some background, and also already Jamie explained about the Jupyter notebook and also capability of this testbed. Similarly, you can see that we import all those important modules for analysis. And then this section shows some of the hazard models here. So we already published this information to our hazard service. There are some IDs you can use it for analysis. This one, we want to show you some visualization here. First one is wave height. So you can see that this wave height hazard data is available. So you can zoom in to see that where this hazard values you can find. You can also change some opacity of this layer for some, let's see that overlay with the underlying layers. Similarly, you can also be showing here is a surge level. So you can zoom in, you can look at the area. You can also control some opacity of the layer like that. So INCOR provides you this visualization method here. And also next step is the building damage analysis. Like Jamie mentions that we are using parametric fragility curve, which is different from other traditional fragility curve here. So we have these 5 parameters currently input parameter to the fragility model. And we are currently support this new fragility curve right now. And we're going to show you also how to visualize and use it. So we have a fragility service. You can acquire the fragility equations. That's the idea of the fragility curve we're going to show you. And then this is the code snippet to visualize kind of 3D of this chart. Especially this one shows that 2-axis here is wave height and surge level. And then the limit state is 0 is fixed here. So you can see the 3D chart of how this fragility curve looks like. You can also change the camera views and rotate and look at this kind of information. So with this parametric fragility curve, we're going to run building damage analysis. It's very similar as a previous one because we are using the same class or building damage class here. And then we set it up the building inventory, and then we run the analysis. And then you see that this is output. You can see here a different number of limit state, different number of damage state. You can use also describe function to look at some statistics of each columns. This one is also showing the map of the building damage plot here for the damage state 0. So now you are able to see that where is, although the dot represent the buildings and also shows some of the building damage and which damage state 0. You can zoom in to look at more detail, the locations and also the values of the building damage. So next one is Galveston has a housing unit allocation, which are available for other test bed and other analysis too. This one is basically mapping demographic information to each building. So it creates a synthetic populations, which are aligning with the demographic information from census. So these are 3 input data sets you can use to run this damage analysis. Now, after that, you run the analysis. What it does is assign the population to each building units. So we're going to look at some outputs here. So you see that each building now have a number of people in population in there. And also we can categorize looking at this based on some demographic information. In this case, we're going to look at the race and ethnicity categories. So you are able to see that how many people for certain ethnicity or the race group belong to. And the next one is also we want to visualize it as a heat map. So you can do that using this code, and then you can run it. You will see very soon they generate the heat map using this population distribution here. So each heat map shows that concentration of the population based on housing allocation analysis. So we're going to use this housing allocation analysis output, which is the population for each building, to use in the population dislocation analysis. So population dislocation analysis give you that each building, it needs to be dislocated or not, so that we are able to count how many people need to dislocate or not. So similarly, you see that we're going to use a chain analysis of previous one. So you can see the building damage analysis from the previous run. You're using housing unit allocation result from the previous run. So it changed to this analysis. After you run it, it runs the analyze the population dislocation. And then let's look at some output here. So we're going to look at this one as a table quickly. So this is just sort of the top 5, and you can see last column shows that this location true or false, shows that need to be dislocated or not. Also, we can visualize this along with the previously we done for ethnicity category also. So if you look at this table, shows that by the ethnicity group, how much need to be, how many people need to be dislocated, how much people does need to be dislocated, and things like that. Thank you. So next, John Vanderlyn going to present about Joplin testbed.
All right, thank you, Joe. Okay, hopefully you can see this. So the next presentation is Joplin, Missouri, a tornado test bed. To give some quick background, the city of Joplin, Missouri, many of you know, but some don't, was hit by a massive EF5 multiple vortex tornado on May 22nd, 2011. It resulted in 161 fatalities and almost 1,200 injuries, significant injuries, at a cost of $2.8 billion in loss. The population of Joplin is about 50,000. However, it's a little misleading because the infrastructure itself, it's a employment hub, a regional employment hub. And so balloons to triple or more of that during the workday. This gives you, you'll see some similar analysis to what you saw presented for Galveston. So this tells us how many owner occupied, renter occupied, and vacant households. Or building, excuse me. So here's just some images from the tornado path that you can see going through here. There's a number of archetypes. The archetypes in this case were developed specifically for modeling tornadoes in INCOR, and so there's a number of supporting papers that, and you can see there's 5 wood residential archetypes, and that's mainly because light frame wood is significantly affected by wind pressures, as you know. And just scrolling through these, a number of papers that modeled that provide the background for that fragility suite that's available in INCOR. This is a slightly better description, and then it tells us how many of those building types are make up the 28,000 that we're modeling in the city of Joplin. And then here you can see them mapped by color. Again, the majority are 1, 5, 9, 12, 18, and 19. And then we also have all the appraisal data and other information. And this allows us to map the archetypes as best we can. Some work, you won't see this today, but some work that you will see in the next release is the ability to implement different retrofit strategies. And so here you can see these are 3 of them. This is in INCOR currently, and it's in a Jupyter notebook, just not being presented today. It's not quite ready. And this would be things like hurricane clips or different types of shingles, things that reduce damage and then subsequently reduce population dislocation and other things that you've heard about already. And then we can look at how many people actually adopt these, and say if it's 10% or 20% or 40% of residents, and put that in randomly and then see what the effect on the damage and the dislocation and the economy would be. Now, of course, we'd never get 100% wishful thinking. We also have the ability to generate random tornado paths across the community, and this allows us to ultimately could do a fully convolved risk. And this comes from a probabilistic tornado hazard analysis that was conducted some years ago. The fragility models themselves, I won't go into this in detail. I know we're a mixed audience of disciplines, but they're processed or physics-based models and apply pressures numerically, to different components of the building, so that we can get the different damage states. And then here we see an example of the fragilities ranging from slight to complete damage. Within Joplin, there's also an electrical power network. So here we see the 18 substations, and Cellular Automata provides us the the building locations that are linked with those 18 substations. So these different colors, these are the buildings themselves, and then the blue dots are the substations. On the top right, this is the social accounting matrix from the computable general equilibrium model, the economics model that you've heard about. And this just shows you some of the entries. There's, of course, a ... indicating that this is quite a bit larger, a number of interacting equations. And so that's a state-of-the-art model developed by the center's economics team. And so this provides what you'll see today, and that's our housing unit allocation, looking at population dislocation, so damage, then population dislocation, and then going into probability of dislocation for each household for this portion, similar to what you saw. And so with that, Jong, I will pass to you for the discussion on INCOR.
Yes, so this is a Joplin testbed. I think that this one shows you a lot of analysis, also similar to the Seaside and Galveston, but it also does have economic analysis also. So first thing it shows is a tornado path. So if you know the hazard ID, you can search on the web page too, then you can display the tornado path like this. This is the one we're gonna use. And this is a building inventories. And this is ID, you can use it. And you could actually visualize to show that all the 19 archetype on the fly here. So you can see the distribution and also the archetype stands for in definition here. And the next one is a frigidity curve. As I showed you previously, we can also look at this all 19 archetype if you want to, but we actually acquire it in locally and then show the 3 frigidity curve. You can see this is a traditional frigidity curve model here. And then using this, we're gonna run some damage analysis. First one is the building damage analysis. Similarly as we using the hazard ID before building inventory data, and we run the analysis, and it will generate this outputs here. And in addition, we're gonna also run some power facility analysis for substation here, and also poles. The reason we are doing that is we're gonna combine these things with the interdependency relationships. After that, similar with the Seaside, we're gonna run some Monte Carlo simulation here to identify the probability of the failure of the buildings and also those electric facilities too. So like I said before, you can set which damage state going to be fall into failure state keys. So we're gonna use a 500 simulation number, and then we run this analysis for the buildings. You can see that we are using the previous run, which is done damage analysis chained here, and then you can run Monte Carlo simulation for buildings. And then afterwards, we also gonna run Monte Carlo simulation for substations using the previous run of the substation damages. And the next one is pole damages using the failure probability using the pole damages from previous runs. And then before we move on to next, we're going to show you a quick map also of the building damages here and using actually failure probability. So you can see that there's a building failure probability aligning with the tornado path here. So one thing you need to remember is now we're going to look at that interdependency to look at how the building functionality changes. So this building functionality analysis utilize the interdependency with the substations and poles. So we're gonna use this interdependency table. We already have the definition of this relationships. And then we're gonna run this analysis. Then what it does is we also use a previous run of building substation poles, the failure analysis. And then after you run it, now you're going to see that some of the building functionality changes here. So if you look at this visualization, you realize that building functionality failure actually spilled over more than just tornado path, because there's some of the substation and poles are damaged within this path that impacted the building functionality. So this visualization shows that changes and impact of interdependency. And also this is just a code to summarize some of the building functionality and non-functionality table you can generate using the pandas library in Python. You can also create a chart similarly. You can say percentage building non-function is 52%, but actually the building's damage is 19%. So you can see that interdependency create some of the buildings non-functional. Next one is we are doing the economic analysis using a computational general equilibrium model. This one uses multiple data sources, index of the household, farms, and relevant government units, and then generate economic analysis. The first thing we need to do is we need to convert that building failure into how to impact on the economy. So what it does is a capital shock analysis we do here. So you can see that we are using this building failure probability from the previous analysis. And then we run this analysis. What it does is map this each building failure into the sectors, economic sector using the CGE model. So you can see these shocks is generated. And we're going to use this shock into the CGE model in the next section. So now we are going to run the CGE model. You can import the CGE model module. And these are all the social accounting models and all input data required to run CGE models. Now you can see here, the line here, we import the capital shock result from the previous analysis. Now you run this analysis. And we are currently using the open source optimization solver called IPOPT. So you're going to see that this is a solver we are using to solve the CGE problem. Now it runs and you can see some iteration going on and it will converge and then it will end with optimization results. Here we go. After that, now we are able to look at some outputs from this analysis. Let's look at the domestic supply changes. So you can see some of the output here. So the column shows that first one is before tornado and after tornado. So you can see that each sector, there's a sum of the domestic supply decrease there. This is a change of the gross income by the household group by their income ranges. So the first column before tornado, after tornado, you can see some of changes here too. This is before tornado of the factor demand is for different labor groups for goods, trade, and others. Next one shows the after the tornado also. You can see some of the decrease also happened because of tornado. And then we're going to show you a little bit more about this analysis here. So you're going to see this first one is domestic supply. Some of the reduction chart is the same as previous one, but you can show the reduction happens after the tornado. These groups have a reduction. Similarly for this factor demand after disaster also changed also. And then lastly, this one also reduction of employment by their household income groups. You can see those employment changes for different household income groups here. So the CGE model provides you some economic snapshot of this impact. Next section is population dislocation model here. So we're going to run population dislocation analysis for the Joplin. It's similar to what we've done for previous test bed. So you can see the similar analysis patterns here, but you can also see the chaining we are using from the previous building damage results we are using here. And then we're going to show you some quick visualization here. This time we try to visualize this population dislocation results with some of the ownership of the building. Before that, you can see that also shows a dislocated or not for each buildings here. And after that, we can aggregate this information with ownership. So you can see ownership number 1 is the housing that you own by the person, and then 2 is a renter. So you can see that depending on the ownership level, you can see the differences of the dislocation or not in this analysis. And also the last table is a summary of the percentage changes. So this is the end of the demo. Just for information again, this Jupyter Notebook already available on INCORE website, incore.ncsa.illinois.edu. If you go to INCORE manual, you are able to look at online version of this Jupyter Notebook. And also you can download the zip file so you can able to run it. And when you do it, you also notice that some of the visualization is missing in the current one, but we're going to update the Jupyter Notebook regularly. So you can have another changes, and also if the new analysis added, we're going to update the Jupyter Notebook on our site. So next release coming up in the middle of May, so you can see more changes coming up. So next, we'll move on to the Q&A session. It's going to be moderated by the Jamie Cruz and Gerardo Rorazel. Thank you.
Hello, folks. If you haven't noticed, there's been a very, very active chat that's been going on. And so some of the questions have been answered within chat, but I wanted to go ahead and address some of those that seem like they either were unanswered or had an awful lot of activity. And so first I'm going to, Charles Scothorn had a question about sort of how comprehensive is the building inventory, or is it user inputted? And also there were many follow-up questions. So I'm going to start with that question and then pass it off to Jared for the next one.
All right, and Jamie, you're not directing that at anyone, so so maybe Jong, do you want to talk about the building inventory, how that's input, and then we can talk about household data because those are two different things.
Yes, so building inventory data, we do have the fixed schema of this table. So we are using geospatial data, either shape files, the most time we are using. So there's some columns are required to run the building damage analysis, especially related to the fragility curve we're going to use, because some fragilities requires to have certain building structure characteristics. One example is age of the building, which computed from when it's built, or some of them also need to have like a surge case, we need to have elevation of the first floor, those information. So in terms of quality of data, we still strengthen and make it better. But depending on city or depending on testbed inventory data, you see the slide of the missing columns and depending on the testbed needs. But we are keeping with the same schema for building inventory data.
And maybe I can add one thing as well. It is essentially user input. So we're not pulling, but we can pull the we can pull the footprints, the heights, things like that, and then. But at some point, there's mapping algorithms. So, for example, we didn't see this today, but for the flood test bed, that can be mapped. But for example, for the tornado test bed, the fragility or the archetypes, I should say, were individually assigned. So that was done with a team working for several days to get through the city of Joplin. I think if that's the answer to your question.
Okay, Jared.
Thanks, Jamie. Yeah, I agree. There's been a lot of activity, flurry of activity in the chats, and it's been kind of difficult to keep up with. But I have started from the beginning and tried to capture the questions that are still remaining. One of the first ones to Dan was, do you incorporate any earthquake or flood insurance information? Also, it would seem many of the infrastructure networks would be dependent on upstream and downstream community impacts. Is that incorporated in the modeling?
Who's the question directed to? Was it for CC?
It was
To you.
Dan, it was for you.
Would you like me? Yeah, Dan. Would you like me to repeat it?
Yeah, I heard several things, so maybe if you could do it.
Okay, so it's a little busy. The first one: do you incorporate any earthquake or flood insurance information into your modeling?
No.
Okay. Also, it would seem many of the infrastructure networks would be dependent on upstream and downstream community impacts. Is that incorporated in the modeling?
And I guess what the question is more like the city of Seaside embedded in a much larger Cascadia subduction zone event. The answer is no. Right now, it's just being considered in isolation.
Okay, thank you.
I'll add to that, Jared, if I can. I think it's a relevant and challenging problem that our researchers are grappling with within the COE, and some of the, I think, forthcoming work that you'll see will be looking at kind of testing multi-scale and multi-resolution modeling for dealing with some of those types of challenges. Although we isolate our primary focus on a target community, looking at how we can leverage perhaps lower fidelity or lower resolution models for looking at the extensive network impacts that cascade from other adjacent regions. But I don't think you'll see that work in any of the existing published test beds.
Excellent. Thank you.
Thank you. Jim Ansbach asked the question, how quickly can current data be input for the purpose of real-time forecasting and response during an event?
So
Yeah, John, why don't you take that? I've got an opinion, but yours is probably more accurate.
Right. I think the current infrastructure is up to user. If a user could create inventory data and then upload and running it, it's a manual process, not going to be automated process right now. So you could do that. But in terms of real-time situation, I think that it's not maybe feasible right away. You could do that. Maybe near real-time may be possible, but still requires to user to generate inventory data to uploading and input it.
Yeah, and I think that was similar to what I was going to say, that you would definitely have to have your community model set up already, and then you could perhaps study, a different approach of a hurricane days out, if that's what you mean by real time. But to do it, do it within minutes would be difficult.
Okay, Jared.
Yes, and we have another question, kind of in a way, in a sense, piggybacking on some of these other questions for the team. Is or how is this information communicated to local leaders, public decision makers? Curious how this very data-driven approach is or is not utilized to inform decision making.
I can take that if people want, or so one of the, in the introduction, when I mentioned that we're going from knowledge creation to implementation, we have 6 partner communities that we'll be working with, and two that you saw today, Joplin and Galveston, are 2 of those communities, and then there's 4 others. And as part of that, we'll be learning more about that process. In other words, what do the communities need NCORE to be able to do to be an effective tool for them? And in return, we'll be improving NCORE at that time. So we're right in that process over the next 4 years, and by year 10, we hope that it'll be a useful tool, usable and useful.
Excellent, thanks, John. I think that covers it.
Okay. The next question, there was Jeff Stokowski asked, what is the time frame of the CGE model in terms of those changes represented after an event?
I believe it's later. We can have one of our economists, Harvey Cutler, might be able to put that in the chat, but I believe it's later that year. So it would be 6-8 months later after things have settled a little bit, approximately.
Okay, Jared.
All right, sure. Yeah, we have another question here. Seaside accounted for building codes and also allowed for mitigation analyses on retrofits. Does Galveston do the same?
But at this point, the primary consideration of the building codes would go into looking at the likely elevation of that first floor member. It's tied to that age parameter and the fragility modeling. However, you won't see in the current Galveston Jupiter notebook the potential to test out different mitigation strategies or alternatives. And that's certainly on our horizon to leverage this test bed to test out some of the optimal decision-making and play out what-if scenarios, including whether it be building codes or different types of policies.
Thank you, Jamie. Mike Miller had a question that generated a lot of conversation. And so I'm just going to repeat the first part of his question, which was quite lengthy. It is, NCORE seems to be very building centric. Does NCORE support the concept of interdependencies relative to multi-hazards and restoration dependencies?
So the short answer is yes, yes, and yes. So we didn't present a lot of that, but you saw in the Joplin example, the electrical power network within Seaside. There's electrical power network, a water network. And then of course, we're linking the things that you can't touch or feel, the things like the social institutions, but the actual services that they're providing and things like that. So INCORE, in my opinion, and would be considered biased, is probably has the best ability of any tool out there to model networks and dependencies with the buildings as well as each other right now.
Thank you, John. Jared?
Thank you, John. We have another question here. Can you please provide details on how cellular automata was used for linking buildings to substations?
Yeah, I can mention that. And in fact, one of the guests today that's on was the programmer of that, actually two of them. And without going into detail, this is from I believe it was a Los Alamos report about 20 years ago. They realized that it was a dynamic process, and so if one substation went out, there was redistribution, and so but needed to know this. So that was a project that they had. So there's a report, and if whoever asked that question, if they want to get in contact with me, I'm happy to direct them to that report that lays that out. But it's if you're obviously the person that asked the question is familiar with cellular automata, so it just uses a basic rule-based process to essentially grab houses based on geometry and rules.
Great, thanks, John. I'll look back and see if I can find the questioner.
Okay. This is from Naveed Atari, and his question is, are there any thoughts on adding AI-based methods to INCORE in the future?
Jamie, I can take that, but do you have any thoughts on that? Have you guys done that for Galveston? We tried for tornadoes.
So I will say, behind the scenes, I think there are a lot of AI and machine learning methods that have been used to derive some of these models. But in terms of directly embedding those algorithms for things like, for example, inventory analysis and development, I think that's where there's some other opportunity in the future. I know we have colleagues that are looking at questions of how can you synthetically simulate some of these types of infrastructure networks, and that may be leveraging some of those types of tools, either heuristics or AI and machine learning as well.
And I think the biggest impact for us that it could have is automating a lot of the data structure, like assigning archetypes. If you have a community of 100,000 buildings and networks based on buildings and roadways, and what we found is instead of AI, at least for archetype assignment, is that just a set of rules, albeit quite complex. It has been better than the AI at this stage, but we'd love to have input and know Naveed well. So if he wants to get in contact, would love to talk to him.
Great, thanks, John. Another question here comes across by kind of testing or validating these against other models. Have any direct damage estimates for these three communities been compared to what would come out of HAZUS?
So we've not, I think, Dan, you've done some comparison for Seaside. In Joplin, we actually compared it because it was a hindcast, so there was a tornado. So we didn't compare it to HAZUS because HAZUS doesn't have a tornado model. But we did compare it to what actually happened in Joplin, and it was, and with the effects, including the CGE, so not even direct, but all the indirect, and so that was the validation, at least the initial validation study of INCORE was for Joplin, and then it became a test bed. But Dan, on Seaside, I think you guys have done some work, I think.
Yeah, well, one of the main things is the fragility functions are from HAZUS. So I think it would be a little bit circular to, go back and compare to it again. So we are using a lot of the momentum flux-based fragility functions from HAZUS. So in that sense, it would be the same.
Excellent.
And
Thank you.
maybe I can point out, and so there's some of the test beds use some HAZUS fragilities, some partially use them, and then some, for example, like the tornado or the flood, do not. So there's quite a bit that was built on that's independent of that.
Okay, David Bonowitz made a reference to the social vulnerability maps that FEMA has created and was wondering if there would be any effort to coordinate with those maps in future studies.
I can take it. I feel like I'm doing a lot of talking though. So there's so we are actually doing some calls. There's no direct coordination on that, but we're doing some calls on loss avoided and things like that with colleagues through coordination with NIST, Mark Leviton at NIST, and FEMA's involved in that. So this may come up. The social vulnerabilities, at least the modeling here, of course, takes into account a lot of physical changes that are happening to the infrastructure as well as the interactions, and so it's fairly complex and modeled at a very detailed household level here. But yeah, we would certainly welcome the opportunity to talk about that.
Great. Another question. Let's see. Discussion has been mostly for buildings, RE infrastructure. Is capacitive analysis possible? For example, for water networks, does INCOR allow hydraulic analysis with damage? Ditto for highways, traffic, electric, power, etc.
I'll maybe give a first response to that and then pass it to some of the other test beds. If I'm correct, I believe all of the current test beds that are published right now look at connectivity-based network analyses. But that's not to say that our center effort is limited to connectivity-based analyses. There are ongoing efforts to look at flow through water, power, transportation systems. And all of those are planned for future INCOR implementation.
I think I'm satisfied with that one. Thanks, Jeannie. No addition.
Okay, there was a question about the number of parameters that could be considered in the parametric fragilities coming from Naveed Atari.
John, correct me if there is an upper limit, but the intention of this shift was to kind of allow us to move from having a somewhat rigid kind of univariate fragility function like some of the traditional HAZUS fragilities where we were looking solely at log normal distributions and CDFs, and allow for more flexibility with implementing different types of distributions or different functional forms without any constraint that I know on the upper limit of those parameters. The practical constraint that I would note, however, is when we're parameterizing these functions, then we do need those ties, those inputs. Either they need to be linked to our inventory, where we actually do have information on, say, the structural characteristics to inform those fragility models, or to our hazard functions and our hazard models, where we need to be able to predict those intensities. Else, we need to have, say, an assumed distribution or uncertain random variable to characterize those parameterized inputs. But in terms of INCOR, I think technically there would be no restriction to that.
Okay, a question came from Nellie, and it says, what if I have data on a regional level? is that going to be applicable to use within INCOR?
Yeah, no problem there. It's just computation. But in fact, we've modeled or are modeling the state of North Carolina. So yeah, you can do something as large as you have the capacity for. And since it's cloud-based, it's pretty large, Jong, I guess you could say.
Yes. However, like maybe it's a little bit slower, but depending on availability of resources.
Hey, Jared.
All right, thank you. Here's an interesting one. We have a question. Who are the intended users for INCOR? The interface seems rather geeky. I speak Python, but many don't. Are there plans to make the GUI more useful for less geeky types? For example, those who don't know Python?
Yeah, there definitely is. In fact, there is a web interface under development for communities. It wasn't on the webinar today, but we'll be talking about it in-house during our semi-annual meeting here later this afternoon within the center. And so there definitely is, and that's under development. And the intended users are it's dual essentially, and the intended users are researchers as well as people like catastrophe modelers, insurance companies, things like that. But then also the communities through this interface that uses some default parameters, and they may have the ability to upload their own data, but the data format will be carefully articulated to make sure that the model runs, things like that. So there's several different groups. We're targeting all of them.
Thank you.
Thank you.
There was a question about where the social accounting matrix that is the foundation for the computable general equilibrium models, where does that come from?
So actually, Jamie, as an economist, perhaps you want to take that one. I can give an engineer's answer, but I think you would be probably optimal for that if you don't mind.
Well, the social accounting matrix is based on sort of current data for those communities. And so it is customized for each community. And from there, then the CGE model with the inputs and outputs is created.
And maybe I'll add on to, I think a lot there you can gather from various sources and pull it all together, but you also have the ability to purchase it at the county level through vendors.
Right, such as Implan, yeah.
Yeah, and Atom and people like that. And so we've done both, because sometimes the amount of personnel time that it takes to create the data set far exceeds, if it's a large county or a large group, it far exceeds the purchase price. So we've done both.
Mm-hmm. Excellent.
Okay.
Yeah, we have one more. Or we actually have several more, but let's see. We're looking at the Galveston testbed. What examples of coupling the social and physical systems models can be noted?
So one example would be where we're leveraging that household allocation model and leveraging the information at the household level to predict population dislocation, but it also is informed by the physical system. So it's looking at dislocation of residents, but it's also dependent upon things like the damage level to the structure, for example. Or we're looking at what we're referring to as hybrid metrics of resilience, which would look at buildings that we don't have access to through a transportation network, and they have non-evacuees inside. So that's a coupling between physical access and then population behavior in terms of evacuation prior to an event. There are other examples in other test beds as well that have not yet been implemented in Galveston that also look at kind of that back and forth coupling in terms of demand shift, because people leave and then that influences the demand on the infrastructure systems.
Thank you. Thank you, Jamie. An early question that was asked, directed at Dan, is in the infrastructure models, does that take into account the upstream and downstream dependencies of that community?
I think this was a comment that Jamie added. I think all of the test beds are, for right now, just within the test bed itself. And we are working towards the inputs and outputs, for example, the power flow into the community, or the water flow, or the transportation flow in and out of the community. But as of now, INCOR is just on the community. I think future work is how do we embed that in a larger regional system.
Great. We have a question from Stephen Gavrilovich. Can you run higher fidelity response damage models for individual assets? For example, an open seas analysis, or are you constrained to fragility functions?
So that's a great question. So when Open Seas was linked with INCOR a few years ago, Michael Scott over at OSU, when he was working with the center, coded that. And John, I remember you obviously worked with him on that. Is that feature still available?
I think we haven't improved it from the last try, but still it's possible because now OpenSea is available in the Python. So it's very easy to combine and work. One thing is then we may need to have a little tweak in the building damage analysis to how to use the result from the OpenSea's analysis.
All right.
Okay, so there was a question from Nellie that I think he was asking, he was asking for sort of more specificity, and it had to do with the regional modeling capability of INCOR. And so the idea is not to use individual building, but more building in a regional level, but sort of more generic data, aggregated. Is that going to be usable within INCOR?
I can answer that. It is possible, but one drawback I think there is usually how to acquire the hazard value on that regional area. So my understanding is the hazard case, they take the centroid of the polygon or boundary to acquire these hazard values. So if you are able to just sacrifice that accuracy of hazard value and just reading the same hazard value for entire regions, I think definitely we could do that.
All right. Perhaps we have one more. We can probably answer this one real quick, and then this will probably be the last question we have time for today, or at least for the session. Do you have a chart or document about what are the interdependencies included until now in INCOR?
So in the examples, yes. So in the that can be found from the tables, but and we're working on additional scientific documentation that'll explain that for each of those. But there's really no limit because it's INCOR. I probably should have mentioned this a little more in the introduction, but I think it's quite apparent now. It's a computational environment, not really software, and so we can go in, develop your own table if you wanted to combine two things and even bring in a different type of infrastructure or model. That's what it's set up for the researchers. So that's the idea behind it.
And also actually add the link to the Navid's paper, which how we derived the interdependency between building and substation using the cellular automata. So the link is on the chat right now.
Thanks, John.
Okay, last question from Christopher Jones, and it's not a limerick. Will INCOR be able to handle events like the Texas February 2021 power grid failure and impacts on the water system?
I guess in theory, it certainly could. I mean, for example, like in the CGE model, this is slightly different, but same concept, within a different field study in testbed, Lumberton, North Carolina, where we have to model the effect of the pandemic on the economy by turning off firms and then having that propagate through all the infrastructure, the households, things like that. So we would use the same logic to model something like that by a probability of a substation going down, or and basically running Monte Carlo throughout the state to have those turn off, and then it would propagate through the economy as well as other things. Now, as far as pipes breaking and things, that's not modeled right now, but it's open source. So if somebody can contribute that'd be great.
Okay, I think this is a great time for us to wind the webinar down. John, do you have any final comments to share with the audience?
Yeah, I'll just say, first, thank you to all the presenters and to the organizers and everybody that contributed to the webinar. And then thanks to all of our guests, as well as in the center and outside of the center. And if your question wasn't answered, please email resilience@colostate.edu, and we'll get it to the right person and get you a response. And again, thank you, and we hope to engage more with you and have you use NCORE. Accounts are free and available to anybody. So thanks to everybody.
Thank you all.
Bye-bye.
Bye, everybody.